Hello, this is mathjazz from Almost Cool. This video is on linear approximation. It is part of a 3-video series where we'll talk about linear approximation, Newton's method, and the differences between the two and common mistakes made when students confuse the two. So, on to linear approximation. Linearization, or linear approximation, is a technique of using the tangent line of a function at a point to find values of a function near that point. So the method here is we're going to use our derivative to find a tangent line at a point that's close to the value we want. And then instead of plugging our point into our function and finding a y value, we're going to plug our point into the tangent line and find a y value. This won't be an exact measure, but I mean that's kind of the point actually, is that finding an exact value would be difficult or expensive or time consuming, and the tangent line would be much easier, much less expensive, much less time consuming, but maybe still good enough for whatever the job is at hand. So this relies on the concept that on small scales, the tangent line looks like the original function. Here is an example of this. This is the graph of x squared and its tangent line at 3. Notice how close the line and the parabola look. Sorry, the parabola is the blue curve and it's the function x squared. The yellow line is the tangent line. If that wasn't obvious. So notice how close the two are to each other near the x equals 3 point. We're going to zoom in right in here near x is 3, y is 10. And let's see, so zooming in just a little bit, we see, yeah, near 2 and near 4 we start seeing some divergence, but even then, the difference between, let's look at this point, looks like 2.2 is where the line goes off the bottom of the screen. The distance between the line's value at x is 2.2 and the curve's value at 2.2 only differs by, it looks like 0.3, which is very small. Now, a 0.3 difference is not so large. Well, it of course depends on the context. A 0.3 difference, but that's the point, is that if you know something about the system that you're working with, and you can know when a difference is large or small relative to your job, then linearization can be a good technique to get values that are close enough for whatever you're trying to do. Oh, let's zoom in just a little bit more. So I think that's the slide we need. Yes. So between 2.5 and 3.5, sorry, 2.85 and 3.05, we have, it's almost perfect. You can barely see any blue at all. If you have a really good resolution, you might be able to see 2 or 3 pixels right at the top and bottom of this segment of the graph, but or 2 or 3 pixels of blue right around here. It's very, very faint, and we see it seems a very good approximation. So here are the steps for linearization. The first step is to find the tangent line at a convenient x value. The final step is to plug in the appropriate x value. That's it. There are 2 steps. There's a first and a last. First is finding the tangent line, and last is plugging in the x value desired into the tangent line. So we're going to try this on this function. A little more complicated than the x squared example we had, but this is very typical for a linear approximation problem. So we're going to find the approximate value of this function at 3.1. The first step will be to find the tangent line at some point near 3.1 that's pretty easy to evaluate. And x equals 3 seems a pretty good choice. So we plug 3 into our function to get our y value. We now know that our tangent line goes through the point 3,0. We find the derivative of our function, plug 3 into that, so we know that the slope of the tangent line is 3, and we plug the slope and the point into point-slope form, and we get y equals 3x minus 9 as our tangent line. At this point, we've completed the first step of the problem, which is finding the tangent line. And the final step of the problem is to plug in 3.1 into our tangent line. So we get y equals 3 times 3.1 minus 3. So that's y equals 3 times 0.1, which is y equals 0.3. So our approximation is 0.3. Thanks for watching. I hope you're enjoying learning calculus. Have a great day. Goodbye.